Welcome everyone. This is the fifth session in the VR in architecture and urban design series. And actually today it's not about VR. So we have extended the scope of this series and we are also going to look into computational design, which actually also fits the focus of our VR lab, which says VR lab, but is absolutely beyond that. We're looking into data-driven, evidence-based design and computational design. So I'm very happy to announce that Patrick Janssen from the National University of Singapore is presenting today. He is a colleague from Singapore, but also sometimes a colleague from Delft. And we have had very interesting discussions actually the last years on what he is developing in Singapore with his online computational design systems, which support or assist urban design. So today Patrick will present for about half an hour, 40 minutes, and then we have time for questions, and we will close this session in 1 hour. If you have any questions, please post them in the chat, or when we are doing the discussion, please raise your hand so I can give you the floor. Yes? So Patrick, welcome, and yeah, good luck with your presentation.
Thank you, Stefan. Thank you very much for this invitation. It's great to be able to present in this forum. And so I'm going to show, over the last 5-6 years, we've been developing various kinds of online tools and systems. And so today I'm going to try and show you some of that work that we've been doing. So I will start with a PowerPoint presentation. So I'm going to share my screen and switch over to the PowerPoint. There we go. All right. So I'm Patrick Janssen, Associate Professor at National University of Singapore, and I have the Design Automation Lab there that focuses on kind of computational processes that support design. So one of the courses that we are teaching, it's both a course that we teach at NUS and also a course that we teach on edX as an edX MOOC, is called Spatial Computational Thinking. And the tools that we've been developing were kind of, they started out as tools for supporting these courses. They've kind of evolved since then, but really the starting point was to try and find a way to teach spatial computational thinking in a way that you could teach it to hundreds or even thousands of people, and that the whole process of writing algorithms, exploring solutions, and working with spatial information, that whole process would be kind of a little more user-friendly and a little bit easier. And so learning procedural coding is one part of computational thinking. And so I think it's one of the, for a novice, it's really one of the difficult, challenging parts. And so the tools that we've developed have kind of focused quite a lot on this issue of learning coding. And so there are people who say that for computational thinking, you don't need to code. I think it's maybe true, but it definitely allows you to really understand computational thinking a lot better if you try and get your hands a little bit dirty and try and do some coding. So in this presentation today, there's a few things I'm going to try and cover. So first, when we are talking about coding and design, we have to comment on Grasshopper, because that is the big guy in the room. And then, so I'm going to give a little bit, very short context on visual programming, and then just show some examples of the kinds of things that students have done in Möbius Modeler. And then number 3, I'm going to try and present some of the ideas behind Möbius Modeler, which is the software that we've been developing. And then while showing those ideas, I'll try and switch to my browser and show some live models. And then number 4, I'm going to talk about Möbius Evolver, which is an optimization software that uses Möbius, and then again go switch to the live browser. So there'll be a bit of switching back and forth from the slides to the browser. So the Möbius, so there's this URL here, mobius.designautomation.net, and the Möbius ecosystem is really a whole bunch of tools that have been built around Möbius Modeler being the main tool that we have been developing. But as things have progressed, we needed all sorts of other tools to support the teaching and the MOOCs and things. So this web page here is kind of a home page for all the stuff to do with Möbius, and Möbius Modeler is then the first link at the top there. And so if you click that, you will be taken to the live software. So in this presentation, I'm not going to, there's lots of things on that list. I'm only going to talk about Möbius Modeler and Möbius Evolver. The other tools on the list there, you can kind of browse the website and try and get some idea from the website. Also, if anybody's got questions, of course, please do ask. So visual programming, let's start with the idea of visual programming. So when we are talking about parametric modeling, there are really there's a whole kind of spectrum of types of parametric modeling. And a few years ago, already 6 years ago, we wrote a paper trying to analyze, trying to find a way of slicing this up into different types. And the way that I wrote this paper with Rudi Stoofs, the way that we ended up doing it was looking at how parametric modeling supports iteration, with iteration being a kind of key a key requirement in the modeling process. So, and then we kind of broke it down into these 4 different types, and a data flow and procedural modeling being the 2 more powerful ones. So with Grasshopper, the iteration is kind of implicit in the data structure, whereas that's the data flow modeling approach, whereas with procedural modeling, iteration is explicit because you actually write for loops and things like that. So when you look at the kind of ecosystem of tools, they just keep multiplying. More and more visual programming tools keep appearing. The first visual programming, well, the first parametric modeling tool which kind of generated 3D models was Houdini in 1980, although or 1982, I think. And then we had General Components and Grasshopper and Dynamo, and now many others. And they all have a similar kind of data flow approach. So one of the, when we started teaching our computational thinking course, one of the questions was, well, should we use this data flow approach? I mean, obviously the ecosystem, the Grasshopper ecosystem is fantastic, and it's, it keeps growing, and it's an amazing tool. But for me, there was something kind of, I wasn't really comfortable teaching computational thinking with this kind of approach that for me often led to stuff that I felt was computationally very sort of confusing. So often you see these Grasshopper networks, they're very large, and then people are kind of proud of the complexity, but really that complexity is like not a good thing in terms of coding. You want to try and have a way of structuring your code that it's much easier to understand and manipulate. So that's where we started, looking at this whole issue of, could there be a different way of doing it? And so we were looking at, this is a paper by Antonio Leitão, who did a paper also on kind of analyzing different kinds of programming languages, both textual and visual. And he had a bunch of students who quite experienced Grasshopper modelers who made a model to generate these forms on the right. And I mean, the models are, you know, quite complex, but on the other hand, they're not that complex. And the Grasshopper networks on the left seem to not be commensurate with the complexity on the right. There just doesn't seem to be, you know, a relationship between the two. So our starting point is to try and figure out, is there a way that we can make it more kind of structured and easier to understand? So really, this was our goal at the time, was, you know, is there a way that we can kind of break this down into much larger kind of a flow? The flow diagram, the flow chart is still a very useful structure, but can we have a flow chart with a lot fewer nodes in it, and where the nodes actually have a kind of meaning when it relates to the model? So when you look at the flow chart, it kind of has a relationship with the model. You can kind of look at the names and think, oh, maybe that does this. Just to give you a kind of idea, I will just show a series of models that were done by my students in NUS in the last couple of years. These models, when you go to the Möbius website, these models are, there's a gallery with all the student work in the gallery, so you can actually look at these models online. But I'm just going to flip through them here so that we don't slow down too much. So Möbius Modeler is basically a 3D parametric modeler that runs in the web browser. It's free, it's open source, you just click it and use it. You don't even need to create an account. So it's as easy as we can make it. So the idea behind Möbius Modeler is that, yeah, you have this flow chart, and the flow chart has a series of nodes connected with arrows, and the model starts at the top and flows through to the end node. And in that sense, it seems maybe a bit similar to Grasshopper, but really the concept is very different when you look more closely. So one of the things is that obviously there's a lot fewer nodes. Every node, there's no ports. So every node, I mean, you can have multiple arrows going into one node, but it doesn't, you know, there's no input ports and output ports. And the thing that is traveling down the wires is a 3D model. It isn't lists of stuff. So there's no lists in Möbius. Now, you know, the idea, of course, is that these nodes with the little kind of text description of what the node is has some cognitive relationship with the model, even for somebody who's never seen the model before. So they can kind of look at it and think, oh, that's interesting. Maybe this relates to that. And so when you break it down, when you click on each node, you see the model. So we, you know, in the course, we tend to teach this approach as well, where you have a very simplified skeletal model at the top somewhere, and then from the skeletal model, so this skeletal model is this one here, creating normal cross curves, and then from that skeletal model we create the different parts, and then they all get merged in the bottom one. So the way that it does this is that inside each node there is a procedure, and that procedure is written in a kind of normal procedural language with you know, all the normal procedural control flow structures and variables and data types. So all that stuff is very similar to textual programming. The only difference is that, well, there is a whole bunch of differences, but one of the main differences in terms of the user interface is that it's a kind of, you don't type the code, you click on stuff and it inserts a line of code, and then there's a input box where you can type things. So this really, for a novice programmers, this really makes it much less error prone. So all the syntax stuff is reduced. You can still make errors by typing the wrong code in the input box, but it's a lot easier to control and to support novices in programming with this kind of approach. So just to flip through some of the models that, so we have a course where you know, they've never done any programming before, and then they have to they have to take a existing building and turn it into a script and write the algorithms for generating the building. And so these are just some examples of the models that they produce during the semester. So the Möbius interface has a dashboard on the left here. And so you have parameters that control the models. All the models are parametric. Changing the parameters will generate different variants of the models. Yeah, I will just flick through these. And all these models are on the gallery. So if you head over to the gallery, you'll be able to see them. So really just to give an idea of the kinds of models they're producing. The students are not urban design students, they're second-year students doing architecture. So most of the models that I'm showing there are not urban models, but of course can also be used in urban situations. So let me now go through the ideas, the things that we've been working with. And Möbius model has been it's on its 10th version. I think it's the 10th version now almost, and we made a lot of mistakes in the beginning, and we've been gradually improving it and tweaking it and trying to make it simpler and easier to use. And so as we've been kind of working through this process, there are kind of some key things that we've kind of done. So I'll just go through these 6 key things and highlight what they are, and then I will switch over and show some live models. So one is functions. So functions, I mean, any programming language has functions, and for us it was very important to have an environment where students could write their own functions. So the system obviously has a whole bunch of functions built in. So in this little snippet here, you can see a flowchart on the left called generate shapes. And it has, a few functions. It has a for loop in it, and it's got, pattern.grid is a function that creates a grid, and then pattern.arc creates arcs. And so there's a few functions in there that are being called. And one of the functions is this one called global.pyramid from polygon. Now that function is actually another flowchart. So the way that these flowcharts work is that every flowchart can be converted to a function and then embedded in another flowchart, and that can be kind of nested as far as you want to go. So it becomes it's a very controlled way of creating complex kinds of models, because you can create a flowchart that does just one part and then save it as a function and then call that function inside another flowchart. So these are called, these kinds of functions are called what we call global functions. They're global user-defined functions. There are also another type, which is a local user-defined function, which I will kind of show later. So topology is another really critical thing that I think we sort of were very keen on right at the start. And so to explain what we mean by topology is basically when you have these geometric objects like points, polylines, and polygons, what we want to be able to do is to go inside those objects and find the kind of components inside them. And so these components are what is the topology. So the topology has 3 layers: wires, edges, and vertices. And basically they're kind of breaking the structure down. So a wire has a bunch of edges, and each edge has 2 vertices. Now the vertices are then linked to positions which actually have a 3D location. So those other things, wires, edges, and vertices, have no spatial location apart from the fact that they're connected to positions. But so what this means is that when you're modeling, you can always, if you have a geometric object, you can dive into it and extract out a wire or an edge or you know, a vertex, and use those for other kinds of modeling operations. So this topology becomes very powerful. And I will come back to this topology when we talk about attributes. So attributes is something that is very normal in GIS and in you know, geospatial modeling. When you're using a GIS system, you know, the attributes are as important as the geometry. So you have some geometry, but maybe the geometry is just a point. And really what is important is the attributes on that point. And so attributes, I've always thought, are incredibly powerful and very, very underutilized in, you know, in the kind of 3D modeling domain. And so you have layers and you have groups, but that's really a kind of very impoverished type of attribute. So in Möbius, we've very much focused on being able to model with attributes, and modeling with attributes is actually kind of essential because that's the whole way that you do anything. And so if we just go back to this topology, basically you can add attributes to any entity in the model. So you can add attributes to an edge or a wire or a vertex. You can add attributes to positions. You can add attributes to objects, you can add attributes to collections. So everything you model can have semantic information added to it. So for example, if you look at this polygon, you can add an attribute to the hole. So you can say, what is this hole? You can say this hole's a window, or this hole's a void, or it's something else. But you can actually add information to your model that describes what everything is. Another common thing in the urban kind of modeling process is that you have a polygon that represents a plot, and you want to know which side of your plot is facing the road and which side is facing the back. So you add an attribute to the edge, and you say, you know, this edge is facing the road. So attributes become very, very powerful, and Möbius has a query language that allows you to query stuff based on those attributes. So you can get stuff out of the model. So you can say, oh, give me all the polygons that have an XYZ position where the Z value is greater than 10. And then it will find those polygons for you. And then publishing, another kind of key concept that we had right from the start, is really this idea that parametric models should be, you know, it should be very easy to turn them into web pages. And so we have a kind of one-click, single-click publishing kind of button inside Möbius, which you just click it and it gets uploaded and turns into a URL. And the URL can either be a URL that you just share on social media, or it can be a embed code. So you can embed it in, you know, Google web page or something like that. Number 5 is viewers. So in your typical kind of CAD system, you know, you always have your CAD viewer, but actually now with the way that, you know, data and the web and the whole kind of way that you kind of interact with these systems, you really want different types of viewers for different purposes. But you don't really want to have them in different softwares. You want to be able to switch from one to the other and easily kind of switch. And for each viewer, like, there's also slightly different performance requirements and kind of goals and things. So the CAD viewer is what we call the CAD viewer, is like the top one. It's really kind of Cartesian space, a big empty space. And you can, it's the one where you can interact most directly with all the topology, and you can click on polygons and select the edges and see what the attributes are and stuff like that. So it's really the most technical one. Then the geospatial viewer is the one with the image tiles, where you get a kind of geospatial context. And the VR viewer is where you have a kind of VR kind of, compared to your previous talks on VR, this is a very simple version of VR, but it gives you a first-person view. And the image at the bottom there is you can embed 360 panoramas inside the viewer, so that you can embed your 3D model inside a kind of realistic context. And then lastly, number 6 is geodata. So geodata is, I mean, there's an enormous amount of data, and this is the slide I was talking about earlier on. So there's an enormous amount of data that, in terms of the design process, is really kind of useful and critical and underused, and needs to be really leveraged a lot more. And I think one of the problems is that in most CAD systems or design environments, you don't have attributes. So even if you can bring in the data, the attributes will disappear and you're suddenly left with dumb geometry again. So one of the advantages of having attributes is that we can bring in geospatial data with the attributes. So both GeoJSON and CityJSON can be imported, and they can be imported at the same time. So you can have a mix of GeoJSON and CityJSON, and all the attributes that are in the data are maintained. So this screenshot here at the bottom, this is the Rotterdam model for CityJSON, and at the bottom here are the attributes. So basically, the kind of structure of the model is maintained. The collections are created, so each building is a collection, and the building then has different surfaces, and the surfaces are in the objects section. So that covers the 6 things that I wanted to talk about as kind of key ideas. So now what I'm going to do is have a look at the time. All right. So I'm going to just show a few of these models, and just to give you an idea of what this kind of feels like. So I'm just trying to see, we have another, so now it is 8:05 over here. So we have another 20 minutes or 15 minutes?
Yes, 25.
20 minutes, 20 minutes.
Including the
Okay.
questions. So.
All right. So so yes, no, that was not the model I wanted to show. Load this one. So let's have a look at which we have a look at. I am going to go a bit faster. View angles. So I mean, as an example, there is this is a kind of a density study that typically we can explore kind of density with the students, looking at different types of density. And so here we're looking at the plot ratio and looking at the view, like a kind of view angle within the street. So changing the view angle, where if the view angle is higher, then your buildings get higher, and if your view angle is lower, then you get lower. And it's calculating the gross plot ratio for the whole area. And so you can create, if you create more buildings, the buildings get bigger and your plot ratio goes up. But if you get fewer buildings, they get bigger, more buildings get smaller, and the plot ratio goes down. So these kinds of tools are quite useful as kind of exploratory density exploration tools to see what kind of densities are achievable with different parameters. And then the fact that you can go here and just click publish and publish it as a web page means that this whole kind of tool can just become something that you don't even need to use Möbius for. You're using Möbius without you knowing it, but basically it's just this flowchart that generates a kind of randomized urban grid, generates the floors, and then does the calculations and things and creates a kind of model out of it. Okay, let's have a look at another thing. So the SG model is more of a data one. So this is where we're importing some GeoJSON data. So it's a model of Singapore, and we can just switch over to the geospatial viewer for this one. So here, if you look at let's go back to here and just look at the attributes. So if you look at the attributes here under polygons, you see that from this GeoJSON data, there's a whole bunch of data that's coming in. And some of the data is the number of people living in HDB, which is housing development flats. And so we're just visualizing that data by extruding the color represents one type of data and the extrusion represents another type of data. And so based on that, we can then visualize the data. So that's just an example of that one. Let me just go and open another one. Rotterdam, let's open that one since that was the one I was showing earlier. So this is the Rotterdam model, city JSON model. So again, I mean, let's have a look at the attributes. So we can have a look at the attributes here and polygons. We can see that under the polygons, we have this type here called attribute called type with a name called roof surface. So if we look at this script here, it's actually got just one node and one line in it, and it's just grabbing the data from Hugo's repository. So we could say, okay, let's say if we want to make this, we want to make the roofs red, then we can go and insert a function here for color, and the entities we want, now we write let me just see if this is big enough to see. I think this is big enough to see. So we write a query where we say PG stands for polygons. I want all polygons where the attribute, what was it called? Type equals roof. And then I'm going to make that red. So now we have red roofs on our, what happened to my model? Yeah. So we have red roofs on all these polygons. So, you know, this is just an example of how easy it is when the model comes in, you can just use this kind of attribute query method to write a small expression that then will go into the model and retrieve the data that you want. So just in one line of code, you can select stuff and do stuff with it. Okay, continuing on, because I want to cover some of the evolutionary stuff.
Mind if I jump in a bit?
Yeah, sure.
I'm sorry, I tried to raise hand, but well, I was a bit
sorry,
late. No, that line of code, is that a standard code you're using? Because I don't recognize it as a SQL query.
No, so we've got we created kind of domain specific language for the querying. So this expression here. So basically what we have this, the language that we've created, we call it OB, and OB gets transpiled to JavaScript and then executed. But OB is it has like Python indexing, and it has a whole bunch of, it's basically what we're trying to do is to, like Python, try and require as few lines of code as possible. So when in our earlier versions of Möbius, everything was a separate line of code, and before you knew it, you had like hundreds of lines of code to do this simple thing. So with OB, there are basically these queries. And so if I want to set an attribute, it's kind of the same sort of thing. So if I want to go in here and set, let's say I've got this collection and I want to create an attribute on it, I say attribute test, and then I can give it a name. And then this then creates an attribute. So there's a kind of a query language and attribute language that now if we look at the collections here, there will be something called test on there.
But so you decided to go with a kind of Python-like structure and not a SQL structure.
For this, yeah. I mean, basically, we looked at the kinds of operations we wanted to do for the spatial modeling, and it was also kind of a performance issue, just in terms of how the data is structured, that we kind of created this very simple sort of querying process. And basically the querying process is actually just a shortcut for this kind of a query get and query filter. So these are the kind of full, these are the functions. And actually when you're doing these shortcuts, you're just, it's just a shortcut for calling these functions. But you can kind of, in the query, you can do multiple queries together. So, you can kind of create, 5 lines of code in one input box.
Okay, thank you.
Yes, load. So let's have a look at just to. Oh yeah, well, okay. Let me have a look at this one. Since I do have a little bit of VR. So since the title is VR, so let's have a look at some VR. So the VR viewer is basically a way of looking at 3D models from a first-person point of view. So it's just the second one is geospatial, the third one is VR. And so if we go into the VR viewer, we can either just walk around in the normal way, and I don't have my headset on, so I can't navigate so well, but it's the normal kind of navigation. And then we have these hotspots where we embed these 360 images from Google Earth, or you can create your own ones, but they're basically like the 360 images that that Google takes from the top of their car. So they're scattered all over the city. So they're quite handy to use those images. And so what we do is we have a way that we have a foreground. We create a duplicate of the image. And so as you can see here, this tree is in front of the buildings, and the people and stuff are walking in front. So it gives this. So you can give this impression of depth. So really, what we're doing is just in a kind of very low-tech way trying to give, a sense of the spatial kind of quality during the process. And so this can be combined with the parametric approach. So, you might be generating different kinds of buildings. So you might have different typologies that you want to explore. And so you're looking at the model from a particular point of view, and you can change the parameters and see in the VR space, you can actually be kind of with your headset on, changing the parameters and exploring the models. All right, let me see, what else did I have on my list of maybe things to show? That was kind of it. So now we want to go and have a look at the evolutionary stuff. So I'm going to have a quick look at my time. Yeah, we're getting a bit tight. So I'm going to give a quick overview of the evolutionary stuff, just to give some idea of what we were doing there, and maybe just, I'm not sure if we'll have time for showing it live. So the evolutionary thing was really about, my research in the past has focused on evolutionary optimization, and so it's always been quite difficult to fit it into the design process. The design process tends to be very open-ended, and you're forking and changing, and the optimization process is kind of very restrictive. So we were interested in using this evolutionary programming approach, particularly because it doesn't use crossover. So in evolutionary programming, you only use mutation. And so when you're doing optimization, you're just mutating the genes. You're not doing any crossover. Now, what this means is that, so before I get to that, what this means, one thing, the other issue, of course, with optimization is it takes a hell of a long time. Typically you click run, and then you wait a day or two, and then you see what happens. So we were really kind of keen with this web-based approach to say, we now have this modeler that we can run as many copies as we want without any license issues. Can we use cloud computing? So we developed this platform on AWS to use Lambda functions. So the functions all get executed in parallel. And so you have one script that's the generative script, one or more scripts that are generative scripts, and you have an evaluation script, and then you upload them, and then, sorry, in just a few minutes you get, it'll evolve, a few thousand designs for you. So compared to kind of other kinds of optimization systems, it's really very fast. So I think I don't want to take up too much time. So sorry, I've got a. So we did, I mean, the idea of this, sorry, I'm just going to mute myself for a second because I've got something going on in my throat. Okay, that was a lot of loud coughing. Okay, now, so what I was trying to show here was basically this process, but where we want to be able to search for solutions, reflect on them, come back, search for more solutions, and at some point change the search space and kind of search again. And so the idea of this evolutionary programming is when we're searching for solutions, we can put in multiple parametric models. So if we just go and have a really quick look at the Möbius Evolver. So the Möbius Evolver interface is all running on Amazon, and so this is a run that I did earlier. So, but it's, you know, it takes a couple of minutes to execute this number of designs. And so it's basically just trying to optimize a urban massing for a number of different performance criteria. And so we have a number of different plots, but the one which is most interesting is this one. So basically at the beginning of the evolutionary process, these two colors here represent two different parametric models. And so we throw them into the evolutionary process and they compete with each other. And then they sort of gradually, one model dies off and the other one survives. So you're evolving both, you know, you're trying to evolve both the type of model and the particular parameters of that model at the same time. So if we go back to the searches here and look at the second one, so then you evolve that for a few minutes and then you reflect on the results and then you say, okay, that's interesting, but now I want to change it. I want to throw in a few more models. So in the next iteration, then we throw in two new models. So at the beginning here, you see two colors again, and then those models sort of compete. And this time, this model here wins. But then halfway through the evolutionary process, we throw in a third model, because you kind of, when you're doing this stuff, you're kind of getting a feeling of, oh, I think maybe this model is going to do better. And then, you know, that model actually ends up winning. So that whole process, kind of interactive conversation, is what kind of this system is trying to. And then each vertical bar here represents the model, and you can view it within the same kind of web app in the viewer here and in the geospatial viewer. And I think that's where I should stop, because now I have 10 minutes left for questions. All right. So let me maybe switch off my screen sharing.
Well, it's a nice slide, Patrick, by the way. Great to see this, and especially also like that you can do this huge analysis, this huge amount of models you can create. And indeed, my last question would have been like, how can you view it spatially? How can you make it something which our students can grab, not only just the graph, but also viewable? But you also showed that. I assume there must be multiple questions for you. So who raises his or her hand?
I had a question. I also sent it to the chat, but I can.
Sorry,
yes,
I didn't.
I see it now. Yes. Can you repeat your question, Laura?
Yeah. So how long will it take for someone new like me to learn the basics of Möbius? And are there maybe tutorials online or?
Yeah, so there's an edX MOOC which is free. You know, the edX MOOCs, you can just join them for free. So if you look on the Möbius.designautomation.net webpage, at the bottom you'll see the edX MOOCs. So there's 3 MOOCs, one on procedural, one on generative, and one on performative. Each MOOC has like 50 videos and a bunch of, so overall there's like 180 videos. With kind of a structured, you can kind of follow it in a structured way, and so, you know, I think is it quick? I don't know. It's I think you know, the thing that we are trying to teach is maybe never going to be quick. We're trying to really, what we want to do is really teach programming in a way that it becomes a stepping stone to other languages, so that after learning Möbius, you can learn Python and JavaScript, which I think for data flow programming has always been an issue, that you become an expert in a particular visual language, but it doesn't lead anywhere. So we are trying to kind of teach programming with all the normal kind of programming concepts. So yeah, it's I think within a few weeks of, you know, playing around on the MOOCs, you can get a pretty good handle on it.
So there's no prior knowledge necessary with Grasshopper or Python or whatever.
The MOOCs are really start at zero. And the first MOOC, the procedural modeling one, crams in like a lot of the basic computational like control flow and data structures and stuff like that. Is all in the first one. So you don't really need to, you know, do all three. You can actually just get started with the first one.
Okay, great. Any other questions? Don't see questions in the chat. Well, in the meantime, then I'm going to ask questions. Maybe some other questions will pop up anyway. How can you exchange what you do with Möbius with other software? Let's say our students mainly work with Rhino or Revit. I assume there will be a standard so you can export it to Rhino and work further there, or how does that work?
Yeah, so we have a OBJ exporter and importer. So that tends to be the format that we use with when attributes are no longer required. So, I mean, I think QGIS, you know, we tend to, when we're bringing in data, we tend to do some stuff in QGIS first, and then so that we not bring in huge amounts of data. So kind of input, we tend to use QGIS, but also, yeah, OBJ for other kinds of models. And so the OBJ supports color, so the models will also have color when they are output. And we have a few two different ways of exporting OBJ models. So there's kind of like a few options there.
Okay. Yeah, and I think the power of the system you're showing is indeed that you have the attributes and the geometry, like in QGIS. And usually you lose that when you work with Rhino or Revit. But can you also create attributes like the models you're showing? If you use the sliders, can you, let's say, produce new data like the amount of square meters, the kind of program or other background information which would be useful for the designers?
Yeah, so that's how we do everything. I mean, everything, like when you're modeling in Möbius, like half the time you're basically attaching attributes to stuff. Attributes are as important as the geometry. So, and so collections can also have attributes. So when you think of a collection in most kind of modeling systems would be like a layer or something. But so we can add attributes to layers. So you can have, so let's say with the city JSON model, right? So the building, each building is a collection, and I can add other attributes to that collection, like the floor area or you know, so I can, for a solar analysis, you know, we add all the kind of performance data to the polygons, but for anything that's to do with the building, we will create a collection and add attributes to the building. If it's a district, we create a collection out of the whole district and add attributes to the district. So everything is you know, right from adding an attribute to a vertex to collections, it's a consistent approach. And even, I mean, everything in Möbius is an attribute. So even the X, Y, Z coordinates of the positions is an attribute. So the way internally that Möbius handles data is just the same way, it's just attributes. So, and there's various functions. So we have these functions to push attributes up and down the hierarchy. So let's say you have a building with floors, you can just push the attribute up the hierarchy to the collection, and it will automatically add up the floor area and create an attribute on the building. So these attributes become sort of kind of powerful technique for doing all sorts of operations. But especially also, basically, we always use the attributes for selecting stuff. So when you have multiple nodes and you're writing a script in one node, the next node in the system will retrieve the geometry using attributes. So the previous node will create an attribute called, you know, type equals wall, and then in the next node you will say, get me all the walls and you know, do something with them. So this attribute system is really an integral part of doing it, because in Grasshopper you have all these lists, right? So in this system there are no lists of stuff. So when you want stuff, you're basically querying rather than using lists. But the advantage of not using lists is you don't get spaghetti. You don't have all these wires going everywhere. You just have two nodes can only be connected with one link.
Yeah.
If I may add to that, you're taking the whole attribute thing to the next level with regards to a GIS system. In GIS, it was already a huge step up from the, let's say, the shapefile model, where you have geometry and attributes separate, to the more database approach, where you have objects which have attributes, and one of the attributes is the geometry. And now you're doing everything can have attributes. So you're really upping the level. And I'm always wondering, a shift in that perspective does always cause issues when, well, as Stefan asked you, how can you exchange data to other platforms? And you have a totally different data model here than is common in all other software that I know. So how do you see the future for this type of data modeling?
So I think, I mean, this question has been, we've been kind of struggling with this issue. I mean, basically, we've always thought of this data structure as a kind of something that can represent all the other kinds of data structures without loss of data. So we can, in theory, we can take a city.json file in, and we can export a city.json file. The export we haven't done yet, but in theory, the data's in there, so we should be able to export it. It's just that if we add data to the edges, let's say we add attributes to the edges, of course, then we can't export it. Now, I think, so we've been looking at two formats, city.json and IFC. And so, and looking at, you know, in terms of the relationships between entities, how we can represent those relationships, and whether we can figure out a way of having a scheme, because basically, let's say I want to create a parametric model and then save it as city.json. What I can do is create a series of attributes, and if I do it all correctly and click export, it will produce a nice city.json. Now, the problem is that humans don't do things nicely. They always screw it up. So you need some kind of schema to check as kind of an integral part. So we kind of need a kind of Möbius schema checking thing, where we can say city.json looks like this in Möbius. You need to have these attributes are required, these are optional, these are, and then when you're kind of modeling, you can say, okay, you know, it can check for you, and then if there's some kind of spelling error or whatever, it will fix it for you. So this is something that, yeah, we're still trying to kind of figure out what might be the best approach. But definitely it's, because we're also thinking about how to convert geometry to IFC. So geometric models and then export IFC, which is a similar kind of issue, even more complicated.
So Patrick, just questioning, is the structure of data related to what you do with Houdini? Is it the same kind of structure? Because there's also a lot of data attributes connected to geometries, and that's the power of that program.
So I mean, basically Möbius came from a kind of merging of concepts from Maya, Houdini, GIS, and kind of a few other things. And so in Houdini, you've got vertices and polygons, and like vertices and what I call objects. You don't have edges, which was always very frustrating in Houdini, not to have edges, and you don't have wires, and you can't add attributes to collections. So again, it's like Eric was saying, we're just trying to take all that stuff and push it and just extrapolate, it's all kind of there, just extrapolate it. Let's just do everything with attributes and see what that gives us and what power we get from that. So yeah, I think that is what we're kind of trying to do.
Especially with the collections where you can level up and go from block level, building level to block level to, let's say, district or region. So
because the collections can be hierarchically nested,
yeah.
So every collection contains other collections.
Yeah. Okay. Yeah, unfortunately, time
we
is
have
up,
run out of time. Yeah.
We can continue discussing this. I have lots of questions as well regarding the integrations, what you can use it for. But I think we have to stop here.
Yeah, I think, I mean, I think it's a research project, so we are super interested in, other people who want to collaborate and join, also PhD students who need to have an open system where they want to develop their own function libraries and things. All those kinds of ideas, we would really welcome any feedback or any suggestions or ideas for collaboration.
Yeah, and it was great you were presenting that here, so introducing it here. You'll be in the Netherlands next week, so
yeah,
for people who want to meet you, it would be great to see you and to discuss this further at our faculty.
That would be great.
Thanks very much. Thank you for joining as well, and hope to see you soon in our next session.
Yes, that would be great. Thank you.